Although AI research is traditionally split into distinct fields like NLP and computer vision, countless real world problems require solutions that integrate information across these modalities. In this video, I'll discuss how we can solve such problems using multimodal embeddings, then show how to use them to do things like zero-shot image classification and image search. And if you're new here, welcome. I'm Shah. I make videos about the things I'm learning about and building in AI. And if you enjoyed this content, please consider clicking the subscribe button. That's a great no-cost way you can support me in all the videos that I make. Here we're going to talk about multimodal embeddings. Although the discussion here will focus around CLIP, which works with text and image data, this is a much more general idea that can be extended to many other modalities. Before talking about multimodal embeddings, it's worth answering the question, what are embeddings? The way I'll define embeddings here are useful numerical representations of data learned through model training. A classic example of this is BERT, which is a popular language model before the era of GPT-3 and all the modern large language models. BERT used to be state of the art, and one of the things that it does is masked language modeling. In other words, you can give it a sequence of text where one of the tokens in that sequence is masked, meaning that it's not visible, and BERT will predict the most likely token that goes in the place of that mask. So if you pass in the sequence listen to your, the most likely token that goes in the sequence is instincts. So it turns out that through learning how to do this prediction, BERT learns useful representations of text, which can be extended to other NLP tasks. The basic idea here is that you'll take BERT and you'll drop its head, so the classification head, which is doing this masked language modeling, and you'll have this mutilated version of BERT, which instead of doing this token prediction, it'll take an input sequence of text and return a numerical representation of it, where each row in this matrix corresponds to each token in this text sequence, and then each of these columns corresponds to the embedding dimension, the dimension of this internal representation of text that BERT uses in order to do masked language modeling. We can go one step further and go from token level representations to sequence level representations. So we could do something like take the average across all these tokens in the sequence, and we're left with a 1 by D matrix, which represents the entire sequence. And of course, to get these embeddings to be a bit more practical, people will often do additional fine-tuning on top of these embeddings, but this is the basic idea of where they are coming from. A key point about embeddings is that these aren't just arbitrary numerical representations. They are typically semantically meaningful, such that if we were to look at how text were organized in this embedding space, similar concepts would tend to be located close together, while dissimilar concepts will tend to be far apart. For example, the sequence a cute puppy might be relatively close to the sequence a good boy, while that same sequence a cute puppy might be relatively far from a sequence like funny cat meme. However, this isn't limited to just text. We can generate embeddings for any type of data. Another popular type of data we might work with are images. So if we had some image embeddings, the space might be structured like this, where we tend to have cats in the top left part, the dogs tend to be in the bottom right part, and then we have a goat further away from these. Although text embeddings and image embeddings are super helpful in that they can be adapted and repurposed to solve other either NLP tasks or computer vision tasks, one major limitation here is that any random text embedding space we might be working with and any random image embedding space we might be working in don't have any relationship to one another. There's no way out of the box to directly map this text embedding space to this image embedding space and vice versa, even if they are semantically meaningful in of themselves. And that's something we can plainly see here in that the text and image embedding spaces are not aligned, because for this text embedding space, the puppies tend to be in the top right, the cats tend to be at the bottom, while while in our image embedding space, the cats tend to be up here and the dogs tend to be down here. But what if there was a way we could merge these two embedding spaces together? That's exactly the key idea behind multimodal embeddings, which are embeddings which align representations of different data modalities. And the basic intuition here is that if we had a multimodal embedding space, we could represent text and images in the same vector space. So now, indeed, text like a cute puppy will be close to images of cute puppies. The text a cute cat will be close to images of a cute cat, and the same thing will hold for other concepts. However, this idea is not limited to just images and text. We could just as easily embed audio and images together. Maybe this is a audio file that is a cat meowing. This is a goat making goat noises. We have a puppy with like a cute bark, and then maybe we have like a funny shrieking sound associated with this cat meme here. Another application of this is aligning representations of brain signals with images and text. What this means is if we were to record someone's brain activity and then represent it in this embedding space, we could in principle decode the brain information to generate images and text. So in essence, reading people's thoughts. Actually, in reference number 4, they are aiming to do exactly this with large language models. Intuitively, this idea of multimodal embeddings is pretty simple to understand. We have this embedding space which is agnostic to modality. So it doesn't matter if it's an image of a cat, a text description of a cat, or the brain signals of someone looking at a picture of a cat. These numerical representations will be relatively similar. But how do we create these aligned numerical representations? In other words, how does this work under the hood? So the key technique behind creating these types of embeddings is contrastive learning, which is an approach that seeks to represent different views of the same underlying information similarly. And the way this works is that we'll train a model on two things: one, positive pairs of data, and two, negative pairs. So in the case of aligning image and text representations, positive pairs might be a picture of a cute cat and a textual caption for this image, and then we might have the text and an image of a cute puppy, and then we might have the same thing for a baby goat. On the other hand, negative captions might look something like this, where you have the image of a cat, but the caption is a cute puppy, image of a puppy, and the caption is a goat, and you have a goat and the caption is a cat. So the intuition here is that we train a model to maximize the similarity between these positive pairs and minimize the similarity between these negative pairs. That's the key intuition. In the following slides, we're going to go one level deeper and look at the loss function and the math behind how this is accomplished. If you don't care about the math and how this is working under the hood, feel free to skip ahead to the example code. But if you're interested in the math, we're about to jump right into it. The way we can use contrastive learning to align image and text representations is we can take images, generate image embeddings using an image encoder. So basically we take our images and generate a single numerical representation for them. And then we can take all these image embeddings and we can concatenate them into a matrix that I'll call I sub E. So this will be an n by d matrix where n is the number of images. So if you have 3 images here, it will be 1, 2, 3. And then d, so the number of columns, will be the embedding dimension. Then we can do a similar thing for text. So we can get a text encoder from off the shelf. We can generate these text embeddings, and then we can concatenate them into a matrix that I'll call T sub E, and that will have the same shape. So we'll have n captions, and then they'll have some embedding dimension D. Just to point out here that the representations that we would put into these matrices won't directly come from an image encoder and text encoder. Instead, these will be multiplied by some learnable weight matrix and then normalized before being organized in this matrix. So that weight matrix that we multiply the original embeddings by are the learnable parameters. Once we have these matrices I and T, we can construct this Logit's matrix. Basically what that means is we're going to take each image in our image embedding matrix and then each text sequence in our text embedding matrix, and we're going to compute their similarity. Typically this is just a cosine similarity, so you do the dot product between these two matrices, and then you'll divide it by a temperature parameter. That's what this tau parameter is representing. And the reason we call them logits is because at some point it's going to be the argument in an exponential function. And we'll see that in a little bit here. So taking just those three examples from the previous slide, the similarity between the first image and the first text sequence will be in this 1, 1 position of the matrix. And then the similarity between this cat image and the sequence a cute puppy will be represented by this value here. Then the similarity between this cat image and the text sequence a cute baby go will be represented by this value here, and so on and so forth. Just looking at this, we can see that what we want is to make the logits on the diagonal of this matrix as big as possible. So in other words, we want to maximize the similarity between the positive pairs, and then we want to minimize the off diagonal elements, which correspond to negative pairs. One way we can do this is via the contrastive loss. So this might take slightly different forms depending on the context or the paper that you're reading, but here I'm going to follow what was done in developing CLIP, which is reference number 3 here. And so basically, one way we can achieve this goal of maximizing the similarity of these on diagonal elements and minimizing the similarity between these off diagonal elements is via this equation here, which is basically saying for the ith image, so let's say this cat image here, we want the numerator to be as big as possible. So the numerator will be the I element. So this will be either 1, 1 or 2, 2 or 3, 3. And then we want the denominator to be as small as possible. So if the numerator is big, the denominator is small, that means this fraction becomes big. And then if we take the log of that, we'll still have a big number. And then we want this number to be as big as possible because the goal of training is to minimize the loss. And then if this number is big and we have a minus sign next to it, then this will be as minimal as possible. That was probably a bit abstract, so let's walk through this step by step. Let's look at just the first image first. With this notation, I call the loss associated with the first image L1. This will consist of taking this 1, 1 logit and then summing over all the logits in this first row. So we're basically taking this image and comparing it to every single caption. Then we do the same thing for the second image. We have the positive pair similarity here, and then we sum over all the logits in this row, and then we do a similar thing for image number 3. So we look at the positive pair similarity, and then we sum over all the logits or similarities in this row. We can do this for every single image in our batch or even in our whole training data set, and then we can aggregate them to get the final contrastive loss. What that'll look like is we'll take the loss according to the first image, the loss according to the second image, and the loss corresponding to the third image, and then we can just take their average, and that'll give us the contrastive loss for the images. But we can do the same exact thing for text. This is how I'm notating contrastive loss for the text. I've switched the index here from J to I, and then I've changed the summation here to I. I feel this notation might be a bit too subtle, but hopefully explaining it step by step, it makes sense what I mean here. So let's see what this looks like for the first text sequence. We're going to be evaluating a cute cat. So we'll look at logits 1, 1 here, and then we'll sum over the logits in this first column. We'll do the same thing for this second text sequence, a cute puppy. And we'll sum over all the logits in this column. And then finally, we do it for the final text sequence. It's important to note here that generally this logits matrix is asymmetric because the similarity between the text, a cute puppy, and this image of a cat is in general different than the similarity between this image of a puppy and the text sequence, a cute cat. That's an important thing to note here, and that's the reason why we go through this whole procedure for the images and the text sequences separately. And then we can aggregate the loss over all the text examples just like we did for the images like this, and then we'll get a total text loss by taking the average of all the examples in our mini batch. We can then combine the image loss and text loss together by taking their average. And then we can write it all out to have this big monstrosity all on one page. But basically this first term here corresponds to the image loss. The second term here corresponds to the text loss. And this is how we train the weights, which translate the raw raw image and text encodings into our multimodal embedding space. This will give us a training signal, which we can use to update the weights of these projection matrices, and just keep doing that until we're satisfied with the loss. So if that was much more math than you were hoping to get out of this video, I apologize for that, but let's jump to practical applications of multimodal embeddings. Here I'm going to use CLIP for two different use cases. This first use case is zero-shot image classification. The meaning of that is we're going to do image classification without explicitly training CLIP to distinguish between the different image classes that we're considering. The first step is to import transformers, and I'm going to bring in these two things, and then I'm importing this PIL library, which will allow us to work with images in Python. Next, we'll load in the model and the data processor. The image preprocessing is important because images could be any type of size and shape and all that. The CLIP processor is an abstraction that ensures the data aren't in a suitable format to be passed through the model. Next, we're going to load in our image. So I'm going to load in this image of a cute cat. So it's the same one we've seen so far. Then I'm going to define the text classes. So this is a really interesting aspect of using CLIP for zero-shot image classification, because before, if you wanted to do image classification, traditionally that was something that was set at model training. It was implicitly coded into the architecture of the model in that you had this classification head, and each value in the output layer corresponded to the probability of class 1 versus class 2 versus class 3, so on and so forth. But now when using CLIP, which is trained via contrastive learning, we actually pass these classes as text inputs. So with our text and image inputs defined, we can pass these through our processor to put them in a suitable format as CLIP, and then we can just pass it to the model. Then with this one line of code, we'll generate these outputs. Then we can extract the logits per image. Recall the logits matrix that we saw a few slides ago, where we had an image and then we had logit values or similarity values between that image and every single piece of text that we passed into the model. That's exactly what we're extracting here. We're extracting the similarity score of the input image to both the text inputs. Then we can convert these logits to probabilities via the softmax, and then this will give us a prediction. What I'm doing here is I'm just doing argmax of the probabilities tensor and using that to pick out the predicted class from this original list that I created. And then I'm just going to print everything like this. So I'll print the predicted class as well as a rounded probability corresponding to that class. With that, the most probable class is a photo of a cat with a associated probability of 99.79%. So it basically nails the classification of this image. But let's see what happens when we use different text classes. Instead of passing in a photo of a cat and a photo of a dog, which are pretty easy classes to distinguish between, let's try something a bit more nuanced, like a ugly cat versus cute cat. And again, here the model basically nails it with 97% probability of this cute cat class. And then we can try something even more challenging, like trying to distinguish if this is a cat meme or not a cat meme. And it indeed gets that it's not a cat meme, but we can see that the probability dropped significantly. Then as a final test of this model, let's see what happens when we pass in an actual cat meme and give it the class choices of cat meme versus not cat meme. And so here the model again nails it. It correctly classifies this as a cat meme with a probability of 83%. And so again, what we're doing here using CLIP is we're taking these three entities. We're taking this text sequence of cat meme, the text sequence of not cat meme, and this image of a cat, encoding them in a shared embedding space, and we're evaluating the similarity between this image of a cat and the text sequence cat meme, and the similarity between this image of a cat and the text sequence not a cat meme. And then we can convert that similarity into a probability as well as a class prediction. The key unlock here is that you are not restricted or limited in the different class labels you can use for image classification. You can be as detailed or vague as you like. You can adapt this to endless different use cases, which is pretty amazing. This second example is basically the inverse of zero-shot image classification. classification. There we had an input image and we wanted to match it with one of the input text sequences. Here in example 2, we're going to do the exact opposite. So instead of starting with an image, we're going to start with a piece of text, in other words, a search query, and then we're going to match it to a set of images. So essentially what we're doing is we're doing a search over a set of images. The way this looks is we'll first load in our images. Here we have a picture of a cute cat, picture of a dog, and a picture of a goat. We'll store them in this image list. We're using the PIL library to open the images and just store them in this list. Then we're going to define a query and process the inputs. Here our query will be a cute dog, and then we'll pass this query along with our image list through the processor, so it's in the appropriate format for clip. Then we'll run these inputs through our model, get these outputs, extract the logits per text now. Before we did logits per image, now we're doing logits per text. So these are going to be the similarity scores between the input text and all the images that we inputted. And then we'll convert these logits into probabilities. So with that, we can evaluate the best match. So I'm doing that again in a similar way. So we have these probabilities doing argmax, which will give us an integer 0, 1, or 2. We can use that to pick out the best matched image, and then we can take the probability associated with that image, and then we can just print everything. So again, the query here was a cute dog, and this is the best matched image with a probability of about 98%. But again, that was a super easy example. So let's try a trickier query like something cute but metal. In this case, the model returns the goat, which is indeed cute, but also goats are associated with heavy metal music, and it got a 77% match probability. Reading this, a good boy, the text itself doesn't have anything to do with animals. You know, maybe it's a human boy and he's well behaved, but a good boy is a colloquialism for dogs that we use often, and the model can pick that up quite easily, so it matches it with a dog with 82% probability. It would be interesting to see if we threw in a picture of a human boy to see how the model would handle that case. This could be something that you do with the example code from the GitHub. And then we can try an extremely controversial query like the best pet in the world. For this, the model returns a cat with a 56% match probability. This is likely indicating that on average, people on the internet love cats more than they love dogs. Nevertheless, it's super interesting how we can use this model in order to do search like this. So those were the two examples. Code is on the GitHub, link in the description below. Let's look ahead to the next video of this series. In the previous video, so part 1, we talked about multimodal large language models. So basically large language models that can process or generate multiple data modalities. In this video, we talked about multimodal embeddings like those generated by Clip, which can be used to do things like image search. So we pass in a query and a set of potential images, and then it'll spit out the best matched image. In the next video of the series, we're going to bring these two ideas together to create a multimodal RAG system. The basic flow here will be to take a user query, like what's there to do in Bali. We'll pass the query into a multimodal retrieval system, which involves using a multimodal embedding model to pick out the documents and images that are most relevant to this query. We'll take the user query and relevant documents and images to generate a prompt, and then we'll pass that prompt into a multimodal large language model, which can process the user query, relevant text documents, and relevant images to generate a helpful response. And as a final note, if you enjoyed this video and you want to learn more, check out the blog published in Towards Data Science. There I went into some details that I probably missed here. And as always, even though this is going to be a member-only story, you can access it completely for free using the friend link in the description below. And with that, thank you so much for your time, and thanks for watching.